Okay, so the last 2 days we spent talking about conditional probability, but mostly with cards. So now we're going to talk about conditional probability with situations. So we talked about the writing of conditional probability is probability of A given B. The formula is equal to the probability of A and B divided by the probability of B. So remember, your probability of A given B means that B has to happen, and within that sample space, what's the probability of A? So your numerator is always the probability of A and B, which means both of them happening, and then you always divide by your sample space. Okay, words associated with conditional probability. So when we read through these problems that are below, we really want to be able to pick out the words that are going to help us understand what it is. So remember before we had the addition rule, which was the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So we know how to find the probability of individual events. We know how to find the probability of two events happening at the same time. We knew that we always use this one whenever we see the word or. Um, we use the independence rule, probability of A and B equals the probability of A times the probability of B whenever we see the word independent. When we know that two words are independent, we know that this must be true, so we use this formula. Sometimes we use this formula in the or formula because of that. So now we have a third formula. So we use the addition rule with the word or, we use the independence rule when we know that something's independent. Now when we see the words if, given, who, also, those are words that are going to trigger us to know that we're talking about conditional. Also, if we go through these problems and we never see the word or, we know we're not using the addition rule. If we go through a problem and we never are given the fact that they're independent, we know we can't use either of those two. We know we have to be using conditional probability, so we can use process of elimination. All right, so let's go through a couple of these examples. So number one, last year at all technical high school, 20% of the students received an academic award. That same year, 16% of the students received an academic award and a service award. What is the probability that a student who receives an academic award also receives a service award? So notice we have the word who and also in here. Notice that in here we never saw the word or, so we know we're not using the addition rule. In here we never saw the word independent, so we can't use that rule, which means by default we have to use conditional probability. So what we need to figure out is what is the condition? What's our sample space? So if we read carefully, what is the probability that a student who receives an academic award also receives a service award? That right there is our condition. Who receives an academic award? So that means that we're going to be saying the probability, we want to know, also receives a service award. So the probability of a service award given academic award. Okay, it's tricky, but it's who receives an academic award. That's like saying, what's the probability a student is wearing what's the probability a student who is in Mr. Luber's class is wearing shorts? The condition is that you're in my class. Okay. So anyways, once we have this given, then we know it's the probability of SA and AA divided by your sample space, which is probability of AA. Okay, so now we have three places that we can substitute in. We have 1, we have 2, and we have 3. Okay, so let's figure out where these 20% and 16% go, and then the X is in the place that those don't go. So 20% of the students received an academic award, so that's just single probability. That's our denominator. So 20%, 0.20. 16% of the students received an academic award and a service award, so that's our numerator. So that's that and right there. Alright, which means if I know those two, then the question is asking us about the conditional, so x equals. If I want to know what x equals, I just divide. So 0.16 divided by 0.2, and I get that x is 0.8, which means that there's an 80% chance. Alright, now, here's the thing. I could actually do this problem completely wrong and get the right answer mathematically, and let me show you why. So let's say I went through here and I didn't realize that this was conditional, and I never saw the word or, so I thought I could use the independence rule. The independence rule says that the probability of AA and SA equals the probability of AA times the probability of SA. So I know AA and SA is 16%. I know the probability of AA is 20%, which means that this must be my variable, my unknown. So to solve for x, I divide by this, I divide by this, and notice that this right here is exactly what I did on the other side. That gave me 0.8, which will be 80%. However, the problem is, if I do this, which I cannot do, so cross that off, I cannot do this because I just assumed independence. Nowhere in this problem did it tell me that these two were independent events. So by doing this formula, I'm saying it is independent, and I got this answer. But I can't assume they're independent, even though it gives me the right answer. So this would be wrong. On your test, this is why when we see you set up this problem, we have to see this, because it lets us know that you didn't do this. Okay, we need to see that you understand that this is conditional versus an independence rule. Okay, all right, let's try it again with number 2. Number 2, a total of 20% of a fire department's firefighters are in the Special Units Division, and 40% of the firefighters in the Special Units Division have a college degree. What is the probability that a firefighter is in the Special Units Division and has a college degree? All right, nowhere in here did we see the word or. Can't be addition rule. So right now we're kind of leaning maybe towards the independence rule because we saw the word and. But nowhere in here do I see the independence rule, so I cannot do that. It would end up mathematically giving me the right answer, but I would miss the idea that this is conditional, and we don't want you to lose all your points on the test. So this is conditional because nowhere in here does it say independence rule or. So it must be conditional. So let's figure out what our condition is. If we read back carefully, it says 40% of firefighters in the Special Units Division have a college degree. Notice it says in the Special Units Division. So out of those, 40% of them have a college degree. So that's our condition. And then we want to know college degree. So it's college degree given Special Units Division. So 40% in the Special Units Division have a college degree. Okay, and then it's the probability of those two together. So and divided by the sample space Special Units Division. So I find where I can replace. 20% of the firefighters departments are in the Special Units Division, so that's my denominator. So 0.20. 40% of the firefighters in the Special Units Division have a college degree. That didn't say and, so it's not my numerator, it's my condition. So 40% equals, which means this must be my x. And I can go back and determine that x is right, because the question was, what is the probability that a firefighter in the Special Units Division, firefighter is in the Special Units Division and, so I knew that that's where my x was going. Remember, anytime that, this is what we need to see on your test. Anytime that you want to solve for x, or anytime that you want to undo a fraction, multiply by the denominator. Those cancel. Multiplied by the denominator. So then x equals 0.4 times 0.2 is 0.08, which means that there's an 8% chance. Alright, let's try it again. So notice in the first one, x was out of 3 places, x was what we were solving for. In the second one, x is our numerator, and now we're going to move it again on you. So a school in Brooklyn surveyed their kids to see what kind of attire they wear. They found that 30% of students are both a junior and wearing a sweatshirt. So there's my 2 events, junior sweatshirt. Also, if a student was wearing a sweatshirt, there was a 60% chance that they were a junior. What is the probability the student was wearing a sweatshirt? So notice my question is asking just for the single event. So I never saw the word or, so I cannot use the addition rule. I see the word and, so I'm thinking independence rule, but I never saw the word independent in here, so I know I cannot assume independence. So it has to be conditional. So I need to figure out what my condition is. Right here, it said the word if. If a student was wearing a sweatshirt. So that's my sample space. There was a 60% chance that they were a junior. So it's junior given sweatshirt equals the probability of junior and sweatshirt divided by the probability of sweatshirt. Okay, remember you're always dividing by your sample space. So let's go back. It says 30% of students are both a junior and wearing a sweatshirt. So that's my numerator. So 0.30 divided by. Also, if a student was wearing a sweatshirt, there was a 60% chance that they were a junior. That's my condition. And then what is the probability that a student was wearing a sweatshirt? That is my sample space. So that's my x. Anytime that I want to solve, this is what I need to see on a test. Okay? That lets us know that you know it's conditional, not independence rule. Anytime that I want to solve or undo a fraction, I multiply by the denominator. X's will cancel. X over here, I get 0.60x equals 0.30. If I want to solve for x, I divide. I get that x equals 0.5 or 50% chance. Alright, so now you've seen in every single one of these we've rotated where the x is. The x has been the numerator, it's been the denominator, and it's been the conditional. Alright? So again, remember as you read through these, or as addition rule, if you can see independence, then you're using the addition rule or the independence rule, but if you do not see either of those by default, or by process of elimination, you're doing conditional. Okay? Alright. Number 4. Andre rolls a pair of number cubes. Number cubes are dice. What is the probability that the sum is 7 if the numbers are different? So that's our condition. So sum equals 7 given different. So if you think about if you roll a pair of number cubes, different means they can't be doubles. There's 6 doubles, which means that there's 30 numbers that are different because there's 36 total in your outcome. If you think about what numbers sum to give you 7, that would be 1 and 6, 2 and 5, 3 and 4. Make sure you write this out. 4 and 3, 5 and 2, and 6 and 1. None of those are doubles. So there's 6 of them. So 6 out of 30, which equals 1/5. Okay? In B, we're going to flip-flop, and we're going to say, what's the probability that the numbers are different if their sum is 7? So probability of different given sum equals 7. If I look at the sample space that I wrote over there, there are 6 where the sum is 7, and out of those 6, every single one of those has different numbers. So it's 6 out of 6, which means there's a 100% chance, or 1. Alright, flip it over. Alright, number 5. You toss a coin 3 times, so we want to make sure we write our sample space. Remember that your sample space for flipping a coin 3 times, there's 8 outcomes. So you have heads, 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 tails, heads, tails, heads. Hopefully you guys are getting pretty good at writing these out. Tails, heads, heads. I'm going to use the sample space for A and B. Okay, so it says, what is the probability that she gets exactly 2 heads if the second toss is heads? So what has to happen is the second toss is heads. So that works, that works, that works, and that works. So the top 2 and the bottom 2. Alright, and out of those, so that's 4. Out of those 4, what's the probability she gets exactly 2 heads? So, exactly 2 heads. So 2 out of 4, which is 1/2. Again, notice that we're limiting our sample space. Right? I'm going to pull this out so we can erase it. Okay. Next, what is the probability that the second toss is head if she gets exactly 2 heads, so we flip-flop the sample space on you. So now we're only looking at the outcomes where there's exactly 2 heads. So this works exactly 2 heads. Notice it doesn't say consecutive. So in this time, there's only 3 of them. And out of those 3, what's the probability that the second toss is heads? That has the second toss as heads, and so does that. So 2 out of 3. Alright, moving on. Okay, so Amy has 1 sibling. Find the probability that Amy's sibling is a boy given the following parameters. So what we want to do is find the probability that Amy's sibling is a boy. This is what we're trying to do. Okay. Well, let's list out our sample space. If Amy has a sibling, that means there's 2 of them. Okay, so if we think about this, that means that mom and dad on their first kid could have a boy, or they could have a girl, and after they have a boy, they could have a boy or a girl. If they had a girl, they could have a boy next, and a girl next. Okay, so if I write out my sample space, that means boy, boy is possible, boy, girl is possible, girl, boy is possible, and girl, girl is possible. So 4 total outcomes. Okay. Parameter 1 says, so we still want to know what the probability is that Amy's sibling is a boy. It says nothing is known about the age of Amy or her sibling. If we don't know anything about their age, that means that Amy is either born first or second. However, we do know that Amy is a girl. So that means that in my sample space, that's not possible. So it's possible that there's a boy and a girl and a boy, or a girl and a girl. Any of those are possible because all we know right now is that Amy is a girl. So that means that there's 3 possible outcomes. Okay, now find the probability that Amy's sibling is a boy. Well, out of these possible outcomes, that could happen, or this could happen. Either Amy's born first, then the boy, or the boy is born first, then the girl. But girl is not what we're looking for, because then Amy wouldn't have a brother. So that's 2 out of 3. Okay? So in parameter 2, we're going to rewrite our sample space. We have boy, boy, we have boy, girl, we have girl, boy, and we have girl, girl. Okay? So it is known that Amy, so we're forgetting parameter 1. It is known that Amy is older than her sibling. Well, if it's known that Amy's older than her sibling, then it means that Amy was born first, which means these don't matter because that's having a boy first. So there's only 2 possible outcomes. Out of those 2, which one makes it so that Amy has a boy? Or, has a brother. That one right there. So 1 out of 2, because the other one would mean that Amy has a sister. Alright? Next one. Alright, so Frank is in sunny Florida for spring break. As he is packing, he is considering what to wear the next 3 days. Suppose that choosing a hat or sunglasses is equally likely each time. Notice he's doing this 3 times. Consider the following events. So notice that if we're talking about something happening 3 times and they're equally likely, that's like having 3 kids, boy or girl. Equally likely, that's like flipping a coin, heads or tails, equally likely. So if we list out the sample space and we're talking about sunglasses or a hat, that means he could have a hat, a hat, sunglasses. He could have hat, sunglasses, hat, or hat, sunglasses, sunglasses. So pretty similar to the heads, tails, or girl, boy. And then, sunglasses all 3 days. Sunglasses, hat, hat. So there's my total of 8 outcomes. Alright, so event A says that the first day is sunglasses, and event B is that there are exactly 2 consecutive days of hats. So, find the probability of A given B. Well, given B means that we're only looking in here where there's exactly 2 consecutive days of hats. So, this has exactly 2. This, exactly 2 consecutive days. This has exactly 2 consecutive days. None of the other ones have exactly 2 consecutive days. So that means there's only 2 possible outcomes. And out of those 2, what's the probability that the first day is sunglasses? Well, that would be this one. So 1 out of 2. Alright. Do this hopefully with a pencil, that way you guys can like star it, underline it, something, and then you guys can erase it afterwards. So that way you can keep using the same sample space, you don't have to start back over again, that'd be a pain. Okay, in part C, find the probability of B given A. So A means that the first day is sunglasses, so that would be 1, 2, 3, 4 in our sample space. And out of those 4, how many of them are exactly 2 consecutive days of hats? Just that one. So 1/4. Determine if A and B are independent. So that means we want to determine probability of A and B equals the probability of A times the probability of B. So let's start with the easy ones. The probability of A. I'm going to take these out of here so we don't see them. Erase these. That's supposed to erase. Okay. Okay, so the probability of A is that the first day is sunglasses. So we can say there's 1, 2, 3, 4. So that's 4 out of 8. My sample space, whenever I talk about independence, will always be my total sample space because it's not conditional, so don't change your total outcomes. Probability of B, I know that there's 8 total outcomes. Probability of B that there's exactly 2 consecutive days of hats. That would be 2 consecutive days exactly, so that would be 2 8s, or yeah, 2 8s. Alright. The probability of both of them happening together, so here's how I would go through this. If you think about it like a Venn diagram, it's your middle. Probability of A and B is your intersection of the two. So I would go through and identify A and identify B and determine which ones overlap. So for instance, the first day of sunglasses is all 4 of these. There are exactly 2 consecutive days of hats. It's this one and this one. And notice that just this one got circled twice. That means that that's the overlap in the Venn diagram, that's the middle. So there's only 1 out of 8. Okay? Well, 1/8 is 0.125, and 4/8 times 1/8 is also 0.125, which means they are equal, which means these are independent events. Remember, independent events means that one does not affect the other. One happening will not affect the probability of the other happening. Alright, last question. Compare probability of A given B with probability of B given A. Well, A given B we found was 1/2, and probability of B given A we found was 1/4. And I can see that this one is more likely, so that's the one that I'm going to talk about. We're going to interpret this in context and with complete sentences. So, A given B, this meant, what was my sample space? So my sample space was that there's exactly 2 consecutive days of hats. So we're going to say, given there were 2 consecutive, I always forget how to spell consecutive days of hats, it is more likely that Frank wears sunglasses on the first day. Okay, so notice I brought Frank back into the problem. I interpreted the fact that 1/2 was more likely than 1/4, and then I interpreted what it meant that what it was that A was given B. Okay, so make sure all of those are in there. There's definitely more ways than one to write this sentence. If you have a question, just ask us. Okay, so biggest thing now is that the problems that we did here in 1, 2, and 3, you're now going to be given all of those types of problems, but with the addition rule, with the independence rule, and now with the conditional. So we have to know what information we can pick out so that we can determine what formula to set up to solve for the problem. Okay? Alright. Have a good weekend, everybody.